Sure, so yeah, I'm all set. So whenever you will say, we will start.
We will start at 11:30,
Yeah,
exactly
yeah.
at 11:30.
Sure, sure.
So we will begin.
Sure, I'm ready. Yeah.
So, dear participants, we are ready to begin the next session now, sequence-to-sequence models by Professor Pawan Goyal. Professor Pawan Goyal is an associate professor at the Department of Computer Science and Engineering, IIT Kharagpur. Prior to joining IIT Kharagpur, he received his BTech degree in electrical engineering from IIT Kanpur and his PhD degree from University of Ulster, UK. And he was a postdoctoral fellow at INRIA Paris. His research interests include natural language understanding, information retrieval, Sanskrit computational linguistics. He has published over 100 research papers in reputed conferences such as ACL, NAACL, so on, and also in journals such as computational linguistics, ACM, transactions, and ACM, TKDE, so on. So he was the recipient of Google India AIML Research Awards 2020 and INAE Young Engineers Award 2020. So now the forum is open to Professor Pawan Goyal.
Thank you very much for this kind introduction and also for inviting me for this session. So, so I assume that I have 1.5 hours, so I'll try to complete by then. So, for the participants, I think it would be good if you can ask your doubts even in between. You don't have to wait for me to complete the session. Will be great if we can have more interactions whenever you are having difficulties. So I'm assuming certain topics that have been done, but if you think there are still doubts in those, you can still ask and we can see if we can go over that. So, okay, so now let's begin this particular session. So the topic I'm covering is sequence-to-sequence models for NLP problems. And here, when I say sequence-to-sequence, I'll focus mainly on RNN kind of models. So these are the recurrent neural networks that have been covered already. And we will see how do you use them for modeling sequence-to-sequence problems. There are other things like after RNNs, there are things like transformers that have become very popular. So transformers are theirs, but I think they will be covered in some other session. So we are focusing mainly on RNN models and how do you use these for sequence-to-sequence problems. And yeah, let's try to understand that. So if you want to read this in more detail, I think there are a lot of resources. So speech and language processing is one of the main books for NLP, and they are working on a 3rd edition draft. So they have this 9th chapter that you will find very useful. And many of the slides that I will be showing are adapted from CS2 to 4, and that is actually the one of the most popular courses for uh, NLP and deep learning. Okay, so now let's start with a quick recap on recurrent neural networks. So when we talk about recurrent neural network, and I will mainly discuss about NLP problems, but we will also see if we can talk about some other things, but while focusing mainly on the NLP part. So what is something that comes out to be different in recurrent neural network than something like the term you might have heard already, vanilla neural networks? They are characterized by an input layer, a hidden layer, and an output layer, right? So input layer is fixed, your hidden layer you choose, and your output layer depends on what problem you're solving. If you're solving classification problem, this would be the number of classes possibly, and so on. So this is the vanilla neural network from where we move to recurrent neural networks, okay? And all these show various possibilities. What are the things you can do with recurrent neural networks? And let's start seeing this one-to-many. Okay, what that means? Your input is fixed. Your input is fixed, but the output as a sequence, the output sequence can be variable length. Right? I can have as much sequence length as I want in the output. Now, what kind of application do you think where this is helpful? That my input may be fixed length input, but my output can be of variable length. So can someone tell me like some particular application you can think of? Input is fixed length, but output can be variable length sequence. You can put on chat, you can unmute and tell. Need not be correct. Need not be correct. You can just tell. Okay, so let me go ahead. I'm still waiting for someone to tell me on this part, one-to-many. Next is many-to-one. Your input sequence, input is a variable length sequence, but your output is fixed. Okay, so I got a response for the first part. So given a sequence, we have sentence, we have to predict the next word of any length. So yeah, so in general, you can say say something like you are given a sentence that is denoted by a fixed length vector, okay? And you have to predict, say the next sentence, predict the next sentence, or generate next sentence, something like that. A more natural application of this is something called image captioning. So if you say image captioning, so image is a fixed dimension input, but you want to generate a caption that can be a variable length. Now, can you give me an example for the second part? Your input is your variable length, but your output is fixed in size. What are the examples for that? And this we can find easily for NLP. Input is variable length, and by variable length means the sequence can have, say, 3 units, a word, 3 words, 4 words, 10 words, doesn't matter. But my output will still remain fixed. What are the examples? Text classification, very good, yes. So you have text classification as a possible application. Your input is a sentence, say in review sentence, and that can be of any length, but finally you want to predict whether this sentiment is positive, negative, or neutral. Okay, so it's again, it's a many-to-one, and there you can use RNNs. Then you have sentiment classification, yes, very good. Then you can, I'm skipping third and I'm going to fourth one. Then you have this many to many, where your input can be variable length, output would also be variable length, but there's a correspondence. There's a one-to-one correspondence between this. So input can be any arbitrary length sequence, but output will be of the same length sequence. Okay, so their sequence lengths are same. Okay, this example is discussed yesterday. So can someone tell uh, what is one particular example for many to many? It was yesterday cap that I'm doing. Speech to text classification, yes. And if you think in terms of NLP, if you think in terms of NLP, that would be something like a NER, name entity recognition. An example would be you're given a sentence, say Sachin is a very good player and so on, and you have to find out in this sentence for each word, is it a named entity or not? Or going in deep, is it a person, location, organization, and so on. Okay? So that you have to do for every particular instance. But then apart from all these is the fourth one, that is many to many. Okay, in many to many, your input can be variable length, output can be variable length, but there is no correspondence, there is no direct correspondence. This can be of size 5, this can be of size 10, this can be of size 12, this can be of size 8. So that is all possible. So you don't have a one-to-one correspondence between the length. And when we talk about sequence to sequence, we are focusing mainly on this particular architecture. Okay, sure. So now one thing that I need for this lecture is something called a language model. Now if language modeling is already covered and you know about it, then someone can just tell me. I will skip this and very quickly. So what is language modeling? So language modeling is a very specific task where you are given a sequence and you want to predict the next word in the sequence. Okay, so something like you are given the sequence, the students opened there, and you have to find what is the next word that would come in the sequence. Would it be books or laptops or exams or minds? And you have to select a word from there. And applications are many you can think of, like all this predictive typing. So you start typing something and it will try to complete, right? But language modeling is one of the very basic ideas in NLP research. So can you get a language model? Okay, and RNN, why it became very popular? Because RNN was a very good language model. RNN can be a very good language model. So what we want to do, overall we want to predict what is the probability of a sequence of words. But that can be decomposed as finding the probability of a given word W4 given a sequence W1, W2, W3. Now, this is what is language modeling. So you are given some previous words and you predict what is the next word that would come here. Now, traditional NLP used to handle it by using co-occurrence and bigrams and trigrams and all that. I won't go into that, but I'll just briefly tell how was this recurrent models trying to help. Okay, so language model is something that will compute, let's say this one. So if I have this, I can use that to compute this. So this is the most basic thing. Probability of a next word given the previous words. Now, if this is already covered, I want one of you to tell me, like, how would you do language modeling using RNN? Okay. So I want to do a language model. Probability W4 given the previous words W1, W2, W3. So how would you use RNN to do this? Using RNN. Okay. You assume a fixed vocabulary. Let's say you have V words in your vocabulary. Oh, let's say W words. I know, not W. Let's say T, because I may need V for something else. So let's say you have T words in your vocabulary. So anybody can tell me how would you use RNN? It may be wrong, doesn't matter, but yeah, some idea. How would I use RNN for doing this task? Predict the next word given the previous words in a sequence. Or
Give the
just tell
input
me.
sequence.
Oh yeah, very good.
Give the
Yes.
input sequence W1, W2, and W3 as input.
Mhm.
Predict the next word, that is W4, using RNN.
Sure. So among these 4 or 5 things that I was showing on this slide, which one would help in doing this? Which of the architecture would help in doing this?
Many to ones.
Many to one. Very good. So you're saying we will simply do many to one. So I will take W1, W2, W3 as input. Now, when I'm taking the input, how would I take the words as input? How do I take input, the words input?
Maybe one hot encoding.
We can take one hot, but you have learned something better than that now.
Word to vex.
We can use word to vector. So let's say I take the word vectors. I take the word embeddings of, say, the students opened. I take their word vectors. And then I have an initial hidden state, and I pass it through to input to hidden, and hidden to hidden, right? So I have 2 different matrices. Now you may have different conventions. I'm just writing something. So let's say this is U and this is W, right? And I get to this particular H1 hidden state. And then I keep on doing that, apply the same U and W. I go to H2 and apply W and U, go to H3. At H3, I now have a matrix that takes me to the classification task. Now, what is the dimension of this matrix that I am taking at this point? What is the dimension of this matrix? Say this particular vector, this output vector. What is the dimension of this output vector? What does it depend on? In many to one, it's a many to one architecture, right? So what does it depend on? The dimension of this particular vector.
Size of the output word.
Your number of classes in your classification, right? So number of classes. So here, because you are doing classifying or you are trying to find probability for each word in your vocabulary, this will be of size T. This will be of size capital T, because I have T words. So, and then you will do softmax and all that, and you will get a probability distribution. So you will finally end up getting a probability distribution. Okay, and you know how to train your model. What is the loss function that you use? Once you have the probability distribution, you would use a cross entropy loss. Cross entropy loss, because you know what is the correct word from your data, and you will compare that with the output. Your cross entropy loss and use that to do backpropagation. So you backprop from whatever units you have to train, you will backprop. And this is again standard backpropagation through time. Use backpropagation through time to backprop. Now this is all about RNN language model. So if you want to see in terms of picture, this is what happens. You feed word embeddings here, you get a hidden state, and you have a distribution over the words and choose the one that has the highest probability. Or if you're doing for training, you simply use the back cross entropy laws to train your bits. So this is where I know what is my many-to-one architecture. Yes, and I can many-to-one architecture for finding the next word, right? Now, how do you train it? You are given a large corpus that will have a lot of text. What you will do, you will keep on, at every point, you will keep on generating the word and get the cross entropy loss, minus
Sir,
log
I have a
probability.
question here.
Yes, please.
Let us assume it is not for classification. I want to predict the next word. Then the output layer, how many number of neurons it is going to have?
So the only way you do that is by doing softmax over your word vocabulary. Okay, there is no way you can generate a new word. I mean, no trivial way of generating a new word. So what happens is that, so you say, okay, I have some information till now that I have compacted in some vector. Now, based on that, I have to generate the new sequence, a new word. You have to do it one by one word at a time. And this word has to be from a known vocabulary. Okay, so here your vocabulary of size t. So you have to find a probability of each of the t words and pick the one with the largest probability. So it's like a classification problem.
Okay, basically where T is size of the vocabulary.
Yes. So as I mentioned, t is the size of your vocabulary.
Okay, sir. Thank you, sir.
So how do you train it? You take a large corpus. That's a good thing about language model. You don't need some annotations. Nobody has to manually annotate anything. You take a large corpus from Wikipedia and from web and start feeding it. And you say, okay, I have the first word, the, that I fed. I have initial state. I have these matrices initialized. I compute this. Then I pass it, get a vector, and I know the next word. I know the next word is students. So I simply compute negative log probability of students from this vector and say, okay, this is my loss at that point without any manual annotation. And then, okay, you feed the correct word. So this particular thing is called, you have heard this term maybe, teacher forcing. So you don't take your output. During training time, you don't take your output. You feed the correct output again, okay, and then you feed it same sequence, get a new distribution minus log probability of opened, and that is your loss. Keep on adding the losses. So keep on adding the losses and use that to backprop. Okay, so it's as simple as that. That's how you can train your language, RNN language model. So fine. Now suppose I have done that training. Okay. Now I have a question. My language model is trained. What does it mean? What does it mean that it is trained? What do I have at the end, as a result of this training? And am I ready to generate some text? Say without any context, I have to generate some text. I have a language model. Yes. First of all, what it means that I have trained my language model. What will I have? Yes.
So I can test it on new data.
Test on new data based on what?
So the weights got updated.
So at the end of the training, what do I have? What is my trained language model? Finally, what is my trained language model? What all things can characterize my trained language model from this figure itself? So by saying that my language model is trained, what I mean is that the three matrices, this, and this, they are trained. That's all. You see, the good thing is that all these generally are not very large and you can fit in a very small memory. Now, the previous language, the NLP language model and Gram language models, they used to be huge. They were of size, say, v to the power 3, where we say t to the power 3. The t is your vocabulary size. So if you are using a 4-gram language model, even a trigram language model, that will be of size tq, because you have to store all possibilities. What is the probability of this word given these two previous words? Okay, so it is huge in storage, but this is linear in size of T. So this is T cross H, H is your hidden dimension, plus H cross H, plus D cross H. So D is the dimension of your MAD. This is all your language model. Okay, now once you have these weights that are trained already, now how you can use that? Say to generate some text. Can you generate some text from out of this? Out of blue, nothing. So you have a trained language model from some data. You want to generate a sentence. How will you do that? I want to generate a new text. And what I have trained, input to hidden, hidden to hidden, and hidden to output. I have already trained these three things, U, V, W. Now, can I generate new text out of that?
Yes, sir.
Okay, how will I do that?
Now we have to give some input.
Yes, let's say I just want to start. Let's say I give a start token. It's a token, it will have some embedding, and I give that input. Okay, and I can give some hidden state. Let's say this can be all zero. They can be all zeros. And because everything is trained, I will get some H1 here. And this is also trained, so I'll get some probability distribution. And from this distribution, I can select a word that is having the highest probability. Say my. And then now you give the output, you feed your output as the next input. And keep on doing that. Find the max probability, say favorite or something. And like that, you can keep on generating your new input. So that means once your RNN language model is trained, then you can generate sentences. Right? So you just take the output, say you sample or take the word with the highest probability, feed it next, and keep on doing that. So you can generate text. So once I understand RNN, I know how to do many to one, and even how to do some sort of text generation. Okay, so I know these two things when I know language models. If anybody has a doubt, you can take it. Otherwise, I'll assume this is all clear. Can someone tell me what is the problem if I just take the maximum probability word here? Say, suppose I just take the max probability word here and feed it next. And then I take the max probability word here, feed next, and keep on doing that. What will be a problem in this architecture?
So it means in the input corpus, whichever word is having more frequency, it is going to be outputted every time. So that will be given to the next recurrent.
May not be based on the frequency. May not be based on the frequency of the word. See, you are saying based on your start token, you assume some word will be will come here. Maybe the word that starts at the maximum number of times, maybe. But that word is fixed. Yes. And then you take that fixed word and generate the next probability word that is also fixed because your model is already trained. So the sequence that you will generate will be deterministic in nature. You cannot get multiple samples out of that. You will get only one fixed sequence every time. So, but suppose you want to get different types of sequences. What change you will have to do? If you don't want to stick to the same sequence again and again, what is the change you will have to do?
We have to retrain, sir.
No, you don't have to retrain. You don't have to retrain. So
Input word should be changed. Sir.
No, even that is not required. Say you
Instead
always
of
start with
start,
a, yeah,
okay.
suppose you start with the start token itself. So you get a probability distribution at the output. Yes, here. And you are selecting the max probability word. You're selecting the max probability word. Now, instead of that, can you do something different? So instead of that, can I say, okay, instead of selecting the max probability word, I'll sample a word. So you know how to sample a word from a probability distribution. So you have a probability distribution, you're not taking the max probability word, but you're sampling them as per their probabilities. So when you sample, you will not always get the word with the highest probability. You will get some words, right, from this randomly. So that's where you can do sampling instead of taking the highest probability word. And that will give you different types of sequences.
But what is the problem with this?
With what?
With taking highest probability word every time?
No, so I was talking about a very simple application, that is you have trained a language model.
Okay.
Okay. Now you just want to use that to generate sentences.
Okay.
Generate arbitrary sentences that look meaningful. Okay.
Oh.
So if I use this maximum probability,
Mhm.
because everything is deterministic, you will always get the same sequence. But if you want to generate multiple sequences, you
Okay,
can
sir.
do that by doing sampling.
Fine, sir.
Now, RNNs can be used for other things also. I think this is all clear now. Sentence classification is simply many to one. I don't have to repeat that, just the final hidden state and apply it for sentence encoding and then do a classification. And they can be used for part of speech tagging. This is another many to many, but where input and output sequence are of the same length. So something like the startled cat knocked over the vase, and you have to tell for each word what is its part of speech: determiner, adjective, noun, verb, and so on. That's a one-to-one. And you can think the same thing for a named entity recognition. That is, in the sequence, what are the named entities at each point? You can again use RNNs for that. Now, I think bidirectional is also very clear to you now. So you can do an R in the forward direction. And similarly, you can do R in the backward direction. And then you can concatenate the two hidden state and use that for your whatever output you are doing. So this is very helpful for many to many tasks like pause tagging or NER, where at every point you may need information from both sides. You may need information from the left, from the right. So you use a left to right, this forward RNN for encoding information from the left, and you use a backward RNN for encoding information from the right, and you concatenate. So this will give you information from both sides and use that for your prediction. So bidirectional RNNs are again very, very helpful. Sure. So now this was just a recap. Okay. Now, so what we have seen, so from an input sequence, we can get a fixed size vector. Example is classification. Input sequence, we can get output sequence of the same length, like NER or part of speech tagging, and so on. Now, can we also do input sequence to an output sequence that is not necessarily of the same length? Okay, and their examples are like machine translation, where you are given an input sequence in English and the output sequence in Hindi or French will possibly not be of the same length. In the question answering have not been tackled a lot with sequence-to-sequence models. It requires some other background knowledge also. Chatbots have been tackled with sequence-to-sequence a lot, and summarization problem. So generally, machine translation, chatbots, and summarization are popular examples for sequence-to-sequence tasks. So your sequence, input sequence is given, you have to produce an output sequence of variable length. Now, let's look at the basics of this sequence-to-sequence, what actually goes inside. But once you have understood the RNN part, I think this would not be very, very difficult. So let's take the example of machine translation. So you are given an input sentence, yes, and you have to predict an output sentence, and that will be in some other language. So it's a source language, and you have the target language. Okay. Now, the question is, how do I handle a task like machine translation with the help of RNNs? So your input sequence is, say, of length nx, and the output sequence is of length ny, and you have to go from nx length to ny length. So when you handle this problem sequence to sequence, generally you talk about it in terms of also something called an encoder-decoder architecture. So what you are saying, your input sequence, you will encode the input sequence into a fixed dimension vector, so encode into some context, and then use that to decode. From there you decode the output sequence. So you can also think of sequence to sequence as encoder-decoder architecture. So you're encoding the input into a fixed dimension vector, and from there you are decoding. Okay. So encoder RNN. So you have an encoder RNN, you have a decoder RNN. Okay. The innovation is that NX and NY can differ from each other. That's all you are doing. So yeah, and this is one way you can see that although we don't use many of these connections, like we generally don't use all these connections, we just say, we don't even give connections. We say, okay, you have the input sequence x1 to xn, x will give me C. Now the C will keep on and will help me decoding y1 to yn, y. Okay. So this is encoder and decoder architecture. Now in terms of what you have already learned in RNN, this looks a very simple extension. So what we are saying, the last state of the encoder RNN will be used as a representation, the encoder representation of the input sequence, and you provide that as an input to the decoder RNN. And decoder RNN is a vector to sequence RNN, a fixed dimension to a sequence, and you can do various experiments on like what kind of connections you can use. But the simplest would be you have a simple connection from this context C to output. Okay. So now let's talk about this again. So I'm talking about a sequence of length nx and output sequences of length ny. I want to go from this, I want to generate, given this input sequence, length nx, output sequence, length ny. How would I do my training for an encoder-decoder RNN? Encoder-decoder RNN. So input is my x1 to x nx, and output is my y1 to y and y. Okay. So how would I take this as input? So yeah, someone can just tell. So how would I get a context C? I have to encode it into context C. How would I do that? This has already been covered even today. So how would I do that? Given an input sequence of length nx, encode that into C.
Word to vec.
So I'll feed individual things as word to vec. Very good. Then they are the word vectors. Then I have some hidden states. Right? And I don't have an output. I don't have an output immediately. So I keep on accumulating this in my hidden states. Okay? And this final hidden state can actually act as my context. And if you think about it, that's what you do in sentence classification. You have a sentence sequence input. You keep on encoding these compute hidden state, and the final hidden state is what becomes your context, and you apply a multi-layer perceptron or whatever on top of that. So this is your context from your input. Now you want to generate based on that. Okay, so encoder part is all fine. So this is your encoder. This is your encoder. You get H and X. Now how will you get your decoder? How will you get your decoder? How would you decode into a sequence of length and y? Yeah.
From the context, use RNN to get the hidden states.
Yes. So you can think of as if you are creating a new RNN here, with this being the initial state, this being at 0 prime. Okay. Now you feed in the start token. You feed in the start token, and you use these two to generate your H1 prime. And from this H1 prime, you generate your probability distribution. And this probability distribution will help you take, so you take the maximum probability word, say max probability word, and that is your first word in the sequence. And then if you are at the test time, you feed it next. And so on. And if you are at the training time, use that, compare with your sequence, and do your compute your loss and do that training.
Sir, I have a question here.
Yes, yes. Yeah.
Again, these two inputs belongs to two different languages.
Yes, yes.
Now, it means how the loss function is framed here.
I'm sorry, which one?
For example, if you consider when using encoder-decoder models for generating the images, since it is from only one distribution, we can use that image. We can take image as input, and we can find this context space or latent space. Then we can generate. We can use the decoder for generating the similar images, similar-looking images. But here, so input is one language and output has to be some other language. So I'm not getting how exactly the model is going to be trained.
Sure. So you see, what are the trainable parameters here? So let's understand. So you have a trainable parameter, say U, X, input to hidden matrix. Then you have this hidden to hidden, say WX. What else? You have this input to hidden again, and that may be a different matrix altogether. So let's say this is my UY. That can be a different matrix. Even the hidden state dimensions that you're using here can be different. Okay, so yeah, but let's not worry into that. Let's say they are same. So VY, and you have this WY. Okay, so okay, and there's only one V. There's only one V because you're not getting any output in the encoder. You're not generating any output. So you actually have quite a few parameters. You have 5 matrices now: UX, WX, UY, WY, and V. And what is the only training signal that you are getting? What is the only training signal you are getting? Okay. See, you are talking about an end-to-end training. There is no prior training. You only know the word embeddings. Say both the languages, you know the word embeddings. And to make tasks simpler, you can possibly think about taking cross-lingual embeddings. So cross-lingual or multilingual embeddings, what they do, they try to put multiple languages in the same space. That would possibly make your task easier, but yeah, that is not essential for this to work. Let's say you have the word embeddings, right? So, but you have to train all these matrices. What is the only input signal that you are seeing? Can you use anything from the encoder to train? Can you use any signal from the encoding side to train?
context there.
So actually, if you think about the end-to-end part, you have to use directly these signals, because the only way your loss is generated is when you generate a word in the decoder, get its probability and take minus log probability of the correct class. That is where you generate your loss. And you can only sum those losses. So your loss comes at the decoder side. Yes. And
Yes.
this loss itself is helping you to train all these parameters. Okay. So this is one reason why neural machine translation required like huge data. You need to have huge data to be able to train this. Okay. So if you have sufficient parallel data, right? The thing is like that. If you have sufficient parallel data, yes, fine. Even if they are different languages, I'll train all my five matrices and I will learn, okay, what should be my ideal way of going from this hidden to this hidden? Or you see, even this hidden to this hidden may help me transform across language. Okay, or you can even try something explicitly, say, okay, I have this final hidden state, I apply a matrix W, a transformation here directly to go to C. W can be of, say, I have a W H cross H, a matrix that goes to C. Okay, and then start from C and compute my other things. And this matrix should take care of transformation between languages. So, do you know how we generally do that transformation between languages? Say, I have embedding for a given word in English. How do I take the find the corresponding word in Hindi and Telugu for that word? How do we do that? Suppose you have to learn a mapping from English to Hindi. Say, I have an embedding for a word in English. Can I get a corresponding word in Hindi, the closest word? How do you learn that mapping? So generally it is done by something called a cross-lingual word embedding field, cross-lingual word embedding. And where what you can do, you can give some examples. Think of it as a regression problem. I have an English word, say night, Hindi word, say raat. I have the individual embeddings. They are not in the same space. That is the problem. The embeddings of individual language are not in the same space. So this and this will not correspond directly to each other. So what they learn a mapping W that, okay, that can transform from the English space to Hindi space. Okay, and this can be learned by giving some examples, say dictionary examples of various words in English and Hindi, and I say, okay, this is the embedding in English, this is the embedding in Hindi, learn a transformation, and that can be trained. So similarly,
such examples are available with us, sir?
Such examples are available with us, maybe very small in terms of dictionaries, in terms of some parallel data. So you can use that to create. But I'm saying even if you don't have those available, you can just declare a matrix like WH cross H. Here, you can just declare a matrix that is a trainable parameter and let the model learn how to train it. So that's what I'm saying. If you have a lot of data, you can depend on the model to learn that mapping between languages by using data. But if you don't have data, that's where the problem comes. If you don't have sufficient data, you may want to give some guidance in terms of, say, already using cross-lingual word embedding. That is, okay, they are in the same space. They're in the same space. Now I can transform. Or giving this matrix yourself, okay, this is a way you can transform from one language to another language. So some of those hacks are required when you don't have sufficient data. But what people have seen, if you have sufficient data, like millions of parallel sentences, you don't have to worry. It will learn. It will learn. I don't know if that is clear. If you have doubt, yeah, we can discuss about it. It's a very important question. But in principle, is that clear that the only loss signal that we get is here at the decoder, and I use that to compute or learn all my matrices. And I am assuming that my model will be trained such that I can learn a mapping from one language to another language by when I go from the previous hidden state, the encoder hidden state to a decoder. I can learn that map.
Sir, for encoder, the input is embeddings corresponding to one language.
Yeah, yeah.
For decoder, it corresponds to some other language.
Yeah, and there you see their matrix is also different. That's why the WS and WI are also very different. They need
Okay.
not be the same. Similarly, going from input to hidden is also different. UX and UI are different.
It means we are not using any kind of dictionary here where there is a mapping.
That's what I'm saying. If you have sufficient parallel data, sufficient training data, you don't have to worry about using dictionaries or whatever. But if you don't have sufficient data, then you have to go to other sort of hacks. Like, can I already train my language model separately and use that directly? Don't do end-to-end training. So many things will come there if you don't have sufficient data. But if you have sufficient data, then you say, okay, I will learn end-to-end.
Sir, I still have a question. Here, the last function for which it is going to now the objective of this decoder is to generate the equivalent words or statements corresponding to the source language.
Yeah, yeah.
Here, but these are not having any access means in terms of a dictionary. Means we
But
don't have
you
any labeled data, labeled kind of
no,
data.
no, no. See, then how are you doing that? You have a label data. You have the input. You have, see, you're training it based on some input data. You have a parallel sentence. This is an English sentence. This is the corresponding Hindi sentence. You have, say, 1 million such pairs. That's where you are training and generating your loss function. So you are getting the max probability word. You're comparing with what is your first word in your sequence.
Okay.
Yes, and taking minus log probability of that.
Okay.
So yeah, you are doing all this supervised. This is all supervised. When you did language modeling, that was unsupervised. You didn't need any parallel data. You just use monolingual data. But here you need parallel data across two languages.
Okay, sir. Now it makes sense, sir.
Okay, okay, fine. So yeah, so you will have this. You will have sentence in one language. You will have sentence in other language. Okay, and you have this parallel data. When you are generating this, you compute your loss based on that. So we have covered this, the encoder RNN, and we have the decoder RNN. So, and you can use that for many different applications. You can use the same thing for say summarization. I am given an input sequence and I have to generate an output sequence for summarization. Similarly for dialogues, I know what is the current context and based on that I have to give a response. And dialogues can be used say in many different applications like customer support or healthcare and so on. So coming back to this machine translation part. So what exactly you are doing? So you compute the probability of a sequence Y given an input sequence X, right? And if you think about it in terms of the probability, that is nothing but you're computing probability of Y1, the first word given the previous input, Y2 given Y1 and X, Y3 given Y1, Y2 and X, and so on. YT given the previous T minus 1 words and X. Now, X is nothing but your condition. That is what is the input that you have seen. And for training this NMT, what you need to do, you have to get a large corpus of parallel sentences where you have sufficient examples of X and Y so that you can train your architecture, all these 5 matrices that we talked about, you can train. So how the training works, so as you see, like this is a sentence from French, you do the encoding. Now at the decoder part, you get the hidden state, get the output, the probability distribution, and take the negative log probability of the actual first word in your sequence. And then you feed the correct word anyway next time, get again the negative log probability of hit, the negative log probability of me, of with, of a, by, and the end of sequence. This is the end of sequence, right? Because I know this is my, this is where my output sequence is. So now these losses will be back propagated through everything, and they are used to learn all these matrices. Okay, so all these matrices are being learned via this loss that is computed at the decoder. So encoder is not directly giving you any loss, but encoder is helping you compute, because you see this value is a function of everything that comes from the encoder. You get to this hidden state, then you are going to this hidden state, and then you are computing this. So you can use that to backdrop again back to all the 5 matrices. So it's a sequence to sequence task, and this is like a single system, end-to-end system, and your back propagation is happening end-to-end. Okay, we don't need anything else. We only need, say, the embeddings of both the languages, or if you're doing a summarization problem, you just need embedding for that particular language for which you're doing summarization. And this encoder-decoder framework finally enables you to learn all these matrices. If there are any question here, just let me know. Now, once you have done the training part, then when you have to generate the translation, right? That's where you are given the input sequence already. You have to just generate the translation. Then you can use the learn matrices. So how will you actually generate the translation? So I have an input sequence, x1 to xnx. I have now trained my model. So I have my encoder trained. So I use the hidden state, generate h1 up to hnx, becomes my encoder, context C. Now from there I am decoding, and I'm putting a star token. Now all my matrices are already learned. And say this is my h1 prime for h1 prime or h1y, whatever you want to call it. And then I have this v. I have got a probability distribution for the output vocabulary. This is now the target vocabulary size. That is the size of this particular vector. Now I can just take the word with the highest probability here, like we did for generating sequence language model. I choose the word with the highest probability. And put it here, y1. And then again, I do this. Now this is just a test. It's a test time. I'm generating some translation. Now I have some question, like when do I stop? I'm taking the word with the highest probability. I'm feeding that, generating another word, and so on. When do I stop this process? Should I continue generating words forever, or can I stop sometime? Is my question clear?
Sir, please repeat the question.
Yeah. So you see, now I have trained my encoder decoder model. So that means all my 5 matrices are trained. Yeah. So now I'm given a sentence, x1 to xnx. In source language, I have to generate a translation of that. So what I was showing, yes, I will get the context here. From there, I will try now generating something. Everything is trained, so I will keep on getting these things. and get a probability distribution. From there, I can sample a word with the highest probability. Sample a word with the highest probability, use it as the next input in this decoder RNN, generate another probability distribution, take the maximum probability word, and do that. Now my question was, when do I stop? When do I stop this process? Because I'm generating things. Can I have some trick to stop generation? That okay, this is sufficient now, I should not generate any further.
Till the size of the input is reached, we can put one constraint.
Yeah, so that's a good thing. So you can say constraint can be, okay, it's of the size of the input. Although you see this may not always work because some languages require more words to size of input, may not be sufficient. Like if you take Sanskrit language, it encodes everything inside morphology, right? When you're going from Sanskrit to English, English is encoding inside words, right? So English would have more number of words than Sanskrit for the same sentence. So it can be something like twice size of input or some heuristic value that you obtain from your data. Or you see, because you're also encoding the end of utterance token. Okay, so you can also see when are you generating end of utterance token in your sequence. So this is now, suppose you generate end of sequence EOS token we are generating. Then you say, okay, I stop, my sequence is ended. So you can say something like, okay, either the end of sequence token is generated, you stop, or you have reached up to this point, you stop. So that is how you can stop. But this is again a greedy decoding. It's a greedy way of selecting. Now, why I am calling it greedy? So think about a sentence that you're translating. And you translate, you see what happens in your decoding. You get the word with the highest probability. Use that as input to get the next word with the highest probability. Say he hit. Again, use this hit as input to generate the word with the highest probability A. But suppose somewhere you went wrong. So you cannot go back. You have to still use this word and feed it as the next word. There is no way you can say, okay, with hit, I could have tried hit me. He hit me with a bat. That, or with a pie, actually, here, with a pie. He hit me with a pie. That would have made more sense. But I just greedily decoded into A here. And that everything went wrong after that. So there's no way in the method that we described so that you can go back and say, okay, no, I went wrong. I should have generated something different. And that is because we are doing greedily, taking the maximum probability. Okay. So what can we do to avoid this problem, this greed decoding problem? So ideally what you want to do, you want to compute probability, that what is the probability of generating this word given the context, generating y2 given y1 and x, y3 given y2, y1 and x, yt given the previous words generated so far and the context x, right? So in general, if you think about, if my vocabulary size is v, yes, and I'm going at t time steps, that is I'm generating t words, 1, 2 up to t words. So you have to take care of all the possibilities and see, okay, which possibility gives you the maximum probability. So each possible way of generating y1. So need not be the maximum probability, because you see, it may happen that one particular y1 is giving you a very high probability. But when you start from y1 and go to y2, this probability is very low. But on the other hand, if you would have taken the second choice, y1 dash, and then you go further, that gives you a higher probability. But in greedy, when you choose greedily, I'm already fixating on y1. I'm saying, okay, I will choose y1. I will not go to y1 prime at all. So I'm missing out on the other sequence that later on might have given me a better translation. So if you have to do it like, if you have to actually get the correct solution, you need to take care of all the possible sequences that you're generating. Okay, you say, okay, all the probability distribution, I have to take care. Maybe the best one here is not sufficient. The second best may be sufficient, or the third best may be sufficient. And keep Okay, and keep using this for the next sequences.
Sir, but it
And
is expensive, sir.
so that's what, it's very expensive. It's b to the power t, but it's b to the power t, because that means you may have to take care of all the words in your vocabulary for all the time stamps, and this is like impossible. This is just impossible. So is there a way between the two? One is greedy part, where you forget anything except the largest probability one, and second, where you take care of everything. What is a way in between? Can I do something in between the two? What do you think?
Maybe one thing is we can randomly sample.
Yeah, see, random sampling here is not a good idea. Why? Because, yeah, I still want to use the high probability things. So I want to still look into the high probability jump. I don't want to go too much into low probability jump. So one thing I can do like sampling, but sampling could be I take top k highest probability words, and k can be small. I say, okay, I will take only top k highest probability word and use all these to say, okay, what is the next word they are generating? And then at that point, I select top k sequences I have generated so far. And this particular thing is actually called beam search based decoding. You use a beam, there's this k is your beam. So I use, say, k equal to 5. I choose 5 possible top highest probable words and then use them further to get the next word and so on. So this is actually very popular in sequence. It's called beam search based decoding. So what is the idea? So on each step of your decoder, instead of selecting greedily the highest probability word, you keep track of k most probable partial translation at that point of time. In practice, people take between 5 to 10. Okay, but depending on your problem, you may have to take a smaller or larger size. So what you are taking care at every point, what is the probability of generating yi given the previous things up to this sequence t, right? Because probabilities are multiplied, so this log probability are added. So you just take the log probability of whatever are being generated up to time step t. So that is your likelihood, log likelihood. Okay, and they are all negative because when you take log of probabilities, this becomes a negative value, right? So they are negative value, and yeah, higher the better. That means if it's a low value with negative, that's better. And what you do, find out top k highest scoring hypothesis. And of course, because we are taking an approximation, we are not using all the VDT things, it will still not give me the optimal solution, but it will be good enough. Okay, much more efficient. So let's take an example. Let's see that we are using only beam size of 2. Okay, and what we are storing, what is the probability of the sequence I have generated so far? Log probability of yi given the previous things. That is given by my probability distribution at the decoder site. So let's see. So I start, at decoder I start. So remember what I will do in my encoder decoder? I go from start, I go to hidden state, and I go to output state, I get a probability distribution. And I choose the word with the highest probability, but instead of doing that, I will choose top 2, because case 2, I'll take top 2 words. So suppose top 2 words are he and I, right? And you see their values are also given. So this is minus 0.7 and this is minus 0.9. Which one is better? He is better. He is having a high probability. So in my greedy decoding, I would have just taken he and continued with that. But in beam search based decoding, what I will do, I will say, okay, I'm not getting rid of I. It may help me later. So I'll say, okay, let me start with he and find out the next 2 words. Let me also start with I and try next 2 words. So in practice, what you will do, so when you were saying I feed the highest probability word, you will try parallelly. In parallel, you will feed he as input and I as input, right? And get the next 2 words. So suppose when you fed he, you got hit and struck. And when you fed I, you got was and got. Again, compute what is the probability up to this point. So this was already minus 0.7 plus what is the probability of hit given start and he. Yes, that will be again in the probability distribution at your decoder. And this suppose gives you minus 0.7. Similarly, this gives you minus 2.9, minus 1.6, minus 1.8. So now you see you have 4 different possibilities. What you should do at this point of time, because this also will keep on exploding, right? This 4 will become 8, will become 16, will become 32. And if your sequence length is long, it's again going exponential size. So what you should do at this point?
Again, we should consider the probabilities, highest
Yes.
probabilities.
Yes. From here, I choose the top 2. And what are top 2? Minus 1.6 and minus 1.7. Right? So I choose this sequence. That means I watch and he hit. And I forget about these 2. And now I continue further. So now I say, okay, this path, he hit, I again pass. And I watch, I again pass. Next. Yes, and I keep on doing that. So, sorry, he hit and I watch, and then you continue. And suppose this gives me these 2. So again, I will not explode, like it will not explode now. So it will always be 4 possibilities, and you have to choose top 2. So you have to always do this. 4 possibilities, choose top 2. So again, you choose top 2. So that will be minus 2.5 and minus 2.8. So actually this path is all gone. Now you are back to this. Okay. And you continue doing this. You continue doing this, generate possibilities, choose top 2. So here, these 2 are the possibilities. And yeah. So with pi is what you have chosen. Again, you will generate. Yes, and then you will choose again. Now, these 2 are possibilities. A and 1. Forget this path. So you will continue from this path, A and 1. Generate further and you get 2 sequences. He hit me with a pi, he hit me with a tart. And suppose you are stopping at this point. This is stopping criteria can be, okay, I have generated maybe end of sequence token after this sentence, or maybe this is the length up to which I want to generate. So your top 2 things. And because you see, you have to generate only one sentence finally. So your sentence would be, he hit me with a pi. This is your sentence. He hit me with a pi. That is your final sentence. But what is interesting, how did beam decoding help you? If you are doing greedy decoding, what would you have got? He. Then the next one would be hit, actually, then me, then with, then a, and then pi. Actually, in this case, even the greedy decoding would have given you the same thing, but just to give an example, suppose I interchange these 2 things. Suppose I say, okay, this was my input. This was minus 0.9 and this was minus 0.7. And suppose these were my initial probabilities. Then you would have got a completely different output. You would have got I was hit and so on. I was hit and so on. You would have gone a completely different track. But by using beam search decoding, in this case, it helped you in getting a path that might have been helpful later. So, yeah, you take the top scoring hypothesis. So this is the one that you output. So again, we need to talk about the stopping criteria. In greedy decoding, you stop until you generate an end token. In beam search, what you can do is, so because you are generating different hypotheses, they may generate end token at different times. So what you can do, whenever a hypothesis gives you end token, it's complete. And place it at some place and continue doing. And usually when do you till when you continue this beam search, until either we have reached a time step t, that okay, I have already generated 10 words, so I'm done, or we have at least n completed hypothesis. That's again a very nice criteria, that is okay, I will keep on doing that until I have n complete hypothesis to choose from, and that's where you stop. Of course, don't do it plain. You still have to put a limit. Otherwise, you may be in a loop, right, where it never ends. So you still have to have some cutoff based on time step. And from these you have to choose. From these you have to choose. Now, one problem comes here is that because you are just taking different hypotheses, and they may have n tokens at different time, so their length may be different. So maybe hypothesis H1 is having length 3, it's only 3 words. H2 is having length 5. So do you see a problem with that? One hypothesis may be smaller length size than the other one. What can be a problem with that? So because you see what you're doing, you're multiplying probabilities, so taking sum of log probabilities. So if you take a larger sequence, obviously this value will keep on decreasing. Every time you will add some negative value to that. So this smaller length things get a favor, like I'd say, get a favor. That is not correct. So to avoid that bias towards the lower length sequences, what we do, we divide this overall probability by the sum of the length. So we say, okay, so we have the log probability that I'm taking sum over the sequence up to 1 to t, but I'm dividing by t. So that now it is normalized with respect to the sequence length. And this is what I use. So I have multiple hypotheses. Among these, I also divide them by the length of the hypothesis and then choose the one that is having the highest score as per this. Okay. Okay. So yeah, so this is the main thing that I had to convey about sequence to sequence, how you can extend the idea of RNN's models for sequence to sequence, and how you can do greedy decoding, and you can also do beam search decoding. If you have any question, I can take this now, because whatever I'm explaining now will be helpful for you when they will be talk about attention models. That is tomorrow.
Yes, now the forum is open for questions and answers.
Yeah, so I can take the questions, and if there are no questions, I'll talk about this attention a bit.
I think there are no questions, sir.
Sure. So then should I continue for another 10 minutes?
Yes.
Okay, sure. So in sequence to sequence models, what we have seen? So we have seen that we have the source sentence input, we get the encoder, hidden state, and from there I start decoding, right? I start decoding. Now the problem here is that whatever input I have, everything has to be encoded in this fixed length vector, right? And from there only I'm decoding. So there is no way, so when I'm generating this, like the poor don't have any money, when I'm generating this word, there is no way I can look back and see, okay, there was a word, corresponding word in French that I could have directly used and generated that. I don't have any access to this word in the input. So that is a problem with this architecture. So this particular encoding needs to capture all the information about the source sentence. And apart from that, I have no access to any of the input words, okay, when I'm doing the decoding. Now, how do I tackle this bottleneck? So for that, there's a very nice proposal of using attention mechanism. So what is the idea? So on each step of the decoder, can you use a direct connection to the encoder hidden states, so that you can also focus on specific parts of the input rather than always focusing on the final encoding. Can I also use focus on different inputs? So in practice, how does it happen? So suppose this is my input. Okay, so let's say x1, x2, x3, x4. And this gives me hidden states h1, h2, h3, h4. And now I'm trying to decode, right? So at the start, I have generated hidden state. Yes. Now what happens in attention? I say, okay, how close is this hidden state to any of the hidden state in my input. So something like, okay, how close is this h1 prime to h1? So to make things simple, assume that they have the same dimension, and you take a dot product. So you take a dot product of this hidden state and this hidden state and get a score. Okay. Similarly, you get a dot product of this and this, you get another score, another score, another score. So they are giving us scores. Now, what are these scores implying? These scores are implying something called how similar is the hidden state at this point to this, and this, and this. And this the model is interpreting as if, okay, how much attention do I have to put at various encoder states? So it takes these scores, and you know how to convert that into probability distribution. So you can do a softmax over there and convert into a probability distribution. And that will give you maybe some state you need to have a higher attention. So you have to put a higher attention here, and some others you have to put a lower attention. Now you get the scores. Suppose they are alpha 1, alpha 2, alpha 3, alpha 4. Now you compute a, so earlier you were directly using this. Now you compute a summarized version of your hidden state, saying, okay, my summary of hidden state is sigma alpha I hi. And what you have done here, you have said, okay, whichever hidden state I should have put a higher attention is given a higher weightage than the other. And then this is what I use. So I take sigma alpha hi, this is my attention output. And this tells me how much attention or what is the summarized information from the input encoder hidden state. Now, how do I use that to decode? How do I use that to decode? Okay, so that's why what I do, I concatenate this. So I concatenate this on top of this, 2h dimension, and use that to do my decoding further, and use that to actually do my decoding. So now I'm getting my actual hidden state, but also I'm getting a summarized information from the input. Okay, and this actually has shown to help a lot with sequence-to-sequence models, this idea of attention. So I concatenate this attention output with the decoder hidden state, and then use these to generate y1 prime. Okay. Now I will take again the next word, get the hidden state, like the normal way I do. But at that point of time, I take a summarized information. And let's say, suppose it gives a high attention to this. That's what I want. I want to generate word like poor. And if it gives a high attention to this word in the input, then I'm done. Then I know, okay, I should put a high attention to this particular input word, concatenate with this, and then generate. And that may help me generate poor. Now, this is the idea of using attention. That is, at the decoder time, whenever you get a hidden state, find a summarized information from the encoder state, how similar they are. Based on that, you create an attention output and put it with this, concatenate with this, use this together to generate my output sequence, output word. So this is your sequence to sequence with attention. In terms of equation, this is again very easy. We have the encoder hidden states h1 to hn, and now suppose we have this decoder hidden state. What you will do? How will you compute the attention scores? You will take st dot product with h1, st dot product with h2 up to st dot product with hn. Now each of them individually will give you a score, and then you compute a softmax over this. So yes, and they are suppose alpha t, softmax over all these scores. And now use the softmax to get a summarized view of the encoder. So you will say sigma alpha I hi. Okay, so this is what you say as your attention output, sigma alpha I hi, and then you concatenate this with your hidden state. And this is your 2h dimension hidden state now to decoder. Use that to generate your output. Okay. And This has helped a lot in various ways. I have just given you a brief glimpse. Attention is going to be covered tomorrow in some other talk. So it has helped a lot in improving at least neural machine translation. And if you see, for example, it gives you some sort of alignment also. So suppose this is your original input sentence and this is your output. If you know what is the word you are putting attention on, so say European, so you know, okay, you can also get an alignment that, okay, I was putting in attention over this word highly. So this is also some sort of alignment that it gives you. See environment and environment, putting alignment. So if you can know what is the word you are putting attention on from the source, it can give you alignment between the source and target sequence. Similarly for summarization. Summation. This is the input and this is the output. And it gives some sort of alignment. That this was giving high attention on this word and so against and combating. They are coming out. Sure. So overall, yeah, overall attention is very impactful. There's a lot of variety in attention. I just gave you the brief idea about it. And there are a variety of models like memory networks. And then there is transformer models that is completely based on attention, that does not use the recurrent connections at all. And yeah, so this is all I had to say. So in our research, we have used that in many, many applications. So for example, like when we talk about Sanskrit language, so we have used there for tasks like poetry to prose conversion. So you know, in Sanskrit, a lot of data is in poetry, but for easy comprehension, you want to convert that into prose. And there are problems on segmentation, Sandhi segmentation and all. And the two sequences are not of the same size. So we tried this sequence to sequence, and again, we did some nice tricks on how do you use attention scores and all. And that was one of the things we had worked for ACL 2019. We had one work there. Similarly, for doing actual segmentation, we try to use that for Sanskrit. Similarly, we use that for error correction. So suppose you are getting an OCR output and you want to convert that into an actual sentence, original sentence, you want to correct the error, you can think of it as a sequence-to-sequence problem. So quite a few variety of problems in Sanskrit language that we tackled using sequence-to-sequence. And of course, we are handling various problems like dialogue models, etc. with this. So yeah, I think this was all I had to say. If there are any questions, I can take up. But yeah, otherwise, I hope I was able to convey some ideas about sequence to sequence.
So,
Okay.
if there are any questions from the audience, you can raise now. So, if there are no more questions, so let me thank Professor Pawan for the illustrative description of sequence-to-sequence models and so on. I am sure that this will inspire our audience in further exploring the field. And I would like to say that tomorrow there is going to be one more session from Professor Pawan on the current trends. So let me thank Professor Pawan. Thank you. Thank you.
Sure. Thank you, everyone. So yeah, we'll see you tomorrow then. Okay. Sure.